So, basis of functions in their graphs. So this first page just simply talks about exactly what we want to cover in this section. What's a function? Well, it's a relationship. Well, what is that? Well, let's talk about it. And then after we deal with this idea of a function, can we look at a graph and determine whether or not that graph depicts a function? We have something that's called the vertical line test, and that vertical line test helps us. That is, if we know what the graph is, we're able to determine that this particular function or relation, rather, is indeed a function or not. Well, first, let's talk about this idea of a domain and the range. We talk about an ordered pair, and you've seen that before, and you've just been bombarded, in grade school all the way up to now, in dealing with relationships. Well, one, numbers, but then secondly, how do numbers relate to each other? Is there a relationship? and what they're saying is, it's just not so much numbers, but they're saying, how do things relate? Whether it's people or whether it's species, whether it's economics, whether it's in natural gas or fluid flow, how do these things relate one to another? If it's economics, how does the cost relate to the so-called supply? Is there a relationship? Well, yes, it is. So we talk about the domain and we talk about the range. So we say that the domain, you're used to seeing, let's say, for example, y equal to, let's say, 2x. Right? And so we say that the set of all x and y for this equation forms a relationship. What relationship? Are they friends? Are they married? Well, it's a relationship. Are they associates? So here we call the x values the domain. And the y values, the range. So in a nutshell, where I'm coming from would be the domain, and then where I'm going, how I'm using those terms to get to where I want to get to. So my destination would be the range. So if there's a relationship, say that we have a set of terms or numbers over here, say x of 1, x of 2, x of 3. And then over here, we say that I'm trying to go somewhere. But where are you going? I don't know, but trying to get somewhere. We say that this is, for right now, let's just say it's some function. And so here that gives us a y sub 1, it gives us y sub 2, gives us some y sub 3. So where I'm coming from, the x values is the domain. So this is some ordered pair of x and y. So x represents the domain, these y values, the so-called range. Okay. Now for just an example of that, let's say we have the number of smartphone users in the United States, and we look at a chart from 2015 to 2018. And you can see a chart here on the left, how the numbers here in millions in terms of smartphone users is about 187 million in 2015, and then by 2018 that number grows to 238 million. So if we take that chart and if we write it in terms of representing the first year as 0, 2015, and then we go up to 2018, so we got 0, 1, 2, 3 in terms of the years. And then we represent on the, that's for the x-axis. And then for the y-axis, we represent the number of smartphone users, just in millions, if you will. And so then we have points of correspondence. That is, we have ordered pair. Right? We have some x value and some y value. So that x value is said to be the domain, and then the y value, it corresponds with that x value. That's the range. And so, again, so 0 here is said to be mapped to 187, and then so on. The first year, 212 million, and so on. Now, we can kind of take, whatever set of data that we're dealing with and form that data information into some kind of relation. Now, our goal today is, does that relation, does it represent a function? Now, why is the function important? Well, the function is important because if I know that the relation is a function, there are neat properties, exact properties that represent functions. Is that function that we take even into the next course and the next course, and then and so on and so on. Well, let's see. So here, the function is a rule of correspondence, that is a mapping. I want to take this x value and I want to map it over to some y value from, let's say, some set A to a set B. Now the set A just represents the domain. That's all that is. Then the set B represents the range. Now the function is said it's just not a relation, but what it does is it assigns to each element of A exactly one element to B. Now what does that mean? Now I'm saying that in that working definition for functions. Oh yeah, by the way, and before the next class, I will post these PDFs in Blackboard, so you can print it out, or if you just want to have it on your screen and use it from there, that's fine. So you don't have to do all the writing in class. You can just add to. So the working definition, I think, helps us to just understand exactly what we're talking about. A function is a relation of ordered pairs such that no two ordered pairs have the same first component. Okay. And we'll look at an example of that to see exactly what does that mean. So again, the set A is the domain. That's the independent values. Now the range values, the y values, they depend on x. So if I choose x, then the y is based on that choice. So we have independent values and also dependent values. So does this relation represent a function? Now, by all means, go back and always we're going to work with this working definition. You know, always look at two-ordered pair, make sure that for all the ordered pair, if I use the first element, I can't use that first element again, right? So if one maps to, let's say, 3, then one cannot map to 6. Now, I can have overlapping for the range, but I can't have that overlapping from the domain, okay? So let's look at this. So here, this says that 1 goes to 6, 2 goes to 6, 3 goes to 8, and then 4 goes to 9. So my question is this relation a function?
Yes.
Yes, it is. So we can have that overlap on that range, but I can't have 1 going to, let's say, for example, 1 goes to 6 and then 1 goes to 8. See that? No. So say yes. All right. All right. So does this relation represent a function?
No.
No, because here I got 6 mapped to 1, and then 6 again is mapped to 2. I have two-ordered pair where no two-ordered pair have the same first component. When I have that, then it's not a function. So we say no, sir. Right? Is everybody fine with that? Right. And hopefully for some it kind of just brings back memories. You know, back when you were in high school at the dance, right? Yeah, right. No. Okay, anyway.
Yes, the dance 3 down.
Oh boy, this is a rough crowd this morning. It's 8 o'clock, right? What do you expect? Oh boy.
I don't wake up till the PMs.
Yeah. Oh boy. So remark. They're gonna give you some problems where they want you to just look at the problem, the equation, and determine whether or not that equation is a function. Just some neat things here. If the equation only has an x squared in it, like y equal to x squared plus whatever 4 or 5, if it's only an x squared, then it's going to be a function. Okay. If there's a y squared in it, it's not going to be a function. So determine whether each equation represents y as a function of x. So we'll say for this first one, we'll say yes. And then for this one, we'll say no because of that. Do you see that? Now, so let's take that first one, and we're going to write it. This is y is equal to 4 minus x squared. Isn't that the first equation? That's A. I just wrote it with respect to y. Now all we're going to do is just find just a few set of ordered pair. Let's see how this works out. So if I pick x to be 1, right? So here, if x is 1, then that's 4 minus 1. I get 3. If I pick x to be negative 1, I still get 4 minus 1. I get 3. So I can have that. There are other numbers there, so you know the range in the domain is bigger than. I'm just selecting just a couple. You can have that. That's fine. Because the first component is different. Now, for this next one, now, let me just pick a different one just to show you in just an easier way. Let's just pick x equal to y squared. Right? So what I'm going to do is here, I can pick y first. If I say that, let's say for example, y is 2. If I square that 2, I get 4 for x. If I pick y to be negative 2, I get 4 for x. Do you see that? See that? So my simple conclusion is, if you see a y square, not a function. Keep moving. Right? And that last statement, it kind of begs the vertical line test that all linear equations are functions except for a vertical line. And we'll talk about the vertical line test in just a second. So the vertical line test for functions, if you can take a vertical line, it's up and down, right? Take a vertical line and go up and down. Sometimes you gotta have to think about that, right? Is that vertical? No, it's horizontal. So vertical line goes up and down. If I can see the graph, here's the thing about the vertical line test, which is kind of crazy because it's begging that you already know the graph. You know, what if you don't know the graph? You know, hello. So, but if the graph is given, and that's what they're going to do in this section, they're going to give you a graph already. They just say, look at the graph and can you determine whether or not this graph represents y as a function of x. So just take the vertical line test. If that vertical line crosses the graph more than once, it's not a function. Basically, it's saying that it's probably some y square in the equation. That's what it's kind of begging for. All right. Okay, help me out with this. Determine whether each relation is a function. State the domain and the range for each relation. So for this first one, is this relation a function? No. Nope, because 3 is mapped to 4 and 5, and then over here 4 is mapped to 4 and 5. So no. Not a good color. Okay. So the domain be 3 and 4. And the range 4 and 5. Again, the domain or the x values, right, and the range, the y values. All right, what about the next one? Is that a function? Yes. Yep. And so obviously the domain, we get 10, negative 2, negative 1, and 5. And the range 4, 1, and 6. Is that okay so far? Good. All right. Evaluate the function at the indicated values and just simplify. What students like to just say, plug in, right? So, no work, right? And here, by the way, this is not critical thinking. Okay, we got to get serious. Okay, so g of negative 1 is equal to negative 1 all to be squared minus 10 times negative 1 minus 3. So that's just 1 plus 10 minus 3. So that's just, what is that, 8? Okay. A. Part B, g of x plus 2. Now, examples like that are important, like this second one here, because in calculus, you have certain equations where things change. There'll be a delta, something added. So you got x, but then you have the next consequence beyond x plus some h, or x plus some delta x. Well, it represents the same idea, that if I can put x into the function and I get a value for y or for the function, then can I put x plus delta x in that function and then still get some output? Well, yes. The way you put x plus delta x in is the same way you put x in, but you just treat x plus delta x, or here x plus 2, as just one term. Let's see. So what that says here, this says g of whatever this is, it's going to replace the x. So this is x plus 2 to be squared minus 10 times parentheses x plus 2 and then minus 3. Do you see that? Okay. Is that all right? Okay, good. So here we FOIL that out, right? So that's x plus 2 times x plus 2. So that's x squared plus 4x plus 4 minus 10x minus 20 minus 3. So g of x plus 2, that's the x squared there. 4x minus 10x is minus 6x, and then the 4 minus the 20 is negative 16 minus 3, negative 19. Is that okay? As the old preacher in Pittsburgh used to say years ago, he would ask the question in his sermon, he would say, "Am I doing okay?" Part C. G of negative x so this is negative x, all to be squared, minus 10 times negative x minus 3. So that just becomes x squared plus x minus 3. And that's the answer. This is not real red. It's better. All right. Evaluate the function at the indicated value and simplify. So do the same thing. So part A, f of negative 6. So we're going to replace the r with negative 6. So this is the square root of negative 6 plus 6 plus 3. Well, the square root of 0 is just 0, and then so this is just 3. Part B, f of 10 is the square root of 10 plus 6 plus 3. So this is the square root of 16 plus 3. Well, that's just 4 plus 3. That's just 7. Okay. Part C, f of x minus 6. So they give us an example like that because I'm telling you, I mean, just throughout calculus, and that's all you're going to see is these changing of x, and that's what calculus is. It is not the static statement, of a quantity. It's the change thereof of a quantity, which represents everything in life, because everything in life is changing. Do you know that you change? You're not the same person you were 3 years ago. I mean, even in body, because after time, you shed. I mean, you're different. Isn't that crazy? Yeah.
Every 7 years.
Yeah, every 7 years. So what the calculus wants to do is to measure that rate of change in everything that's around us. Fascinating. So this is the square root of, I'm going to replace here the r with x minus 6. So this is x minus 6, but the equation already has a plus 6 there. That's under the radical, and then outside is plus 3. So the minus 6 plus 6 cancels out. All you have left is just the square root of x plus 3. And that's it. Now, you want to, you know, in this level now where we're starting you here in this class and beyond, and some of your answers will come out in variable expressions. That's fine. You know, back in school, you know, especially in math class, you're trying to find out, what's the answer? What's the answer? You know, I got 3. I got 4. How dare you say, I got x, or I got the square root of x. And you say, hey, that's not finished. Well, it's okay. Your answer can be a variable, right? So use the vertical line test to determine if y is a function of x. So using the vertical line test, you say yes, is that right? Yes. What about this one?
No.
Nope. Because it crosses twice. What about that one?
Yes.
Well, this one?
Yes.
Yes. Yep. What about this one? That's that vertical line. We said that all linear equations are functions except for a vertical line, because obviously by default it fails the vertical line test. Duh, right? I wish y'all would wake up. No, I'm just joking.
A little bit more coffee.
Ma'am.
A little bit more coffee.
And see, here's the thing. For the last 3 or 4 days, I've just put myself off coffee because it was just too good. Well, that's
I
it.
worked nights at a sports bar. I didn't get home till 2 o'clock in the morning.
Oh, bless you. This past last night?
Yeah.
Oh, bless your heart. Yeah. Well, let me see if I can get some better jokes, right? To help keep you up. Mercy. Wow, I'm so sorry. So what about this guy right here?
No.
No? And what is that called anyway? That's a what?
A circle.
No.
Yeah, an oval.
So some say a circle, some say an oval, some say an egg. Oh, eggs are good, especially right about now, right? But anyway, it's what about an ellipse? Does that sound familiar? Who cares, right? It's too early. So, right, so to know, and what this is, yes? Okay. Use the graph to determine A, the function's domain, B, the function's range, the x-intercept, and do you remember how to find the x-intercept? To find the x-intercept, it's like, you know, algebra is so cool because algebra deals with opposites. You know, as my kid would say, it's backwards. So to find the x-intercept, you let y equals 0, solve for x. All right. Find the y-intercept, let x equals 0, solve for y. So just note that. And as if it's an equation. If it's not an equation, if it's a graph, you just look at where the graph crosses the x-axis, and you're done, right? Here, if the graph is given, find the point where the graph crosses the x-axis. Okay? So, now, here's something that's important. You see that arrow, those arrows there? What does that mean?
Go on forever.
That's right. They go on forever, right? So that forever is some kind of infinity, whether it's negative or positive. So if we're going up, it's positive infinity. If you're going down, it's negative infinity, right? If you're going to the left, it's negative infinity for x. If you're going to the right, it's positive infinity, right? For the arrows. Okay. So here for A, for the domain, what would the domain be for this graph?
Infinity? Or positive infinity? Negative? Wait, oh.
Okay, so say it again.
That's the, I thought that was the intercept.
Part A is the domain. The domain will be the x values that define the function. So now remember that these arrows, they keep going up, and as they go up, they go out, right? And this one goes up and out. So that's going to cover from negative infinity to positive infinity for the x value. So the domain will be the entire number line from negative infinity to positive infinity. Everybody see that? It's those arrows. It's those arrows. Okay. Part B. What about the range?
-4 to positive infinity.
So that's another way to think about it. The domain are the x values that define the function or define the graph. And then the range would be the y values that define the graph. So the y values, look at the y-axis, look at the graph. It goes from -4, always go from least to the greatest, -4 to positive infinity. That's the range. Home on the range. Anyway. I didn't do so well at singing. And that includes -4, right? So you do a bracket. -4 to positive infinity. So part C, the x-intercept. So what's the x-intercept? And it says, if any, and it could be 1, could be more than 1, could be none, right? So what are the x-intercepts?
-3 and 1.
Okay. So you said -3 and 1. Let's say it like this: -3, comma, what's the y value? Huh? 0. If it's the intercept, that means we're letting one of those values equal 0, right? And then 1 and 0. Because in my math lab, they're going to ask, to put that maybe as a point. So if you just say -3 and just say 1, they're going to mark it wrong. So you have to, put in there parentheses -3, comma, 0, close up that parenthesis here. D. Well, if the x-intercept is where the graph crosses the x-axis, the y-intercept is where the graph crosses the y-axis. Very good. See, x is 0, y is -3. Man, y'all are so good. This is a great class. This is wonderful. Okay, and then it says E, the missing function values indicated by the question mark. So that's what down there below f of -2. We just look at the graph for that. So we find x equal -2. Then we come down here, and I'm there. So what is that? -2, comma, -3. So we say equal to -3. And then f of 2, so we find x equal to 2, and we go up. Looks like it's here. 5, yep. Okay. Now let me pick one more and then we'll be done. I want to pick one where they don't have the arrows. See, they got the arrows on that one. That works exactly the same. Arrows on that one. Okay, this is a good one. Okay. Oh, so what's the domain for this guy? Ooh, I want to hear this. You like Hulk Hogan? You remember Hulk Hogan?
-2 to +6.
Am I dating myself? Anyway. Yes, ma'am.
-2 to +6.
We have somebody serious who came to class, right? Let's talk about Hulk Hogan and WrestleMania. But no, I'm just you're good. -2 to +6. See that? The X values that define the function. Now, is it parentheses or brackets? Brackets, because it's the closed dot. See how they get you? And they get you on that little small stuff, you know? And that's what kills me too, you know? Because I mean, I go in there, I have to go in there before you all, and I'm working these problems in my math lab. I'm like, why am I getting this wrong? Anyway, but so close bracket, -2, it's time to go. 6, and then B, the range. So the range, I'm looking at the graph with respect to the graph. So what'd you say? -2 to 6. Oh, that's funny how they did that. That doesn't necessarily work like that all the time, right? So you kind of want to be careful about, is that a pattern for always? No. So good. Part C, the x-intercept is at 4, 0. Then D, the y-intercept. See, that was the x-intercept here. The y-intercept 0, 4. And then E, f of -1. We find x equal -1 on the graph. What is that, 5? Okay, very good. I think we're good.